So in this video, we're going to talk about the fundamental theorem of calculus part 2, or sometimes it's called second fundamental theorem of calculus. But basically, we need to start with saying this new introduction of a type of function that we can consider an accumulation function. Right? So f of x is equal to the definite integral from constant a to x of f of t dt. And so if we remember from our definite integral that it's really just talking about the area under the curve. And so if I were to draw this here and I drew a function that looked like this, and we wanted to talk about f of, from a to some value x, right? So here's x. Well, we would be talking about this area in blue, and so we get a value based off of this area in green here. All right, and so if we add up this area, we'd be able to find out what f of x was. If we're below the x-axis here, right, this here would be a negative value, and if we're above the x-axis, this here would be a positive value. And when we see a graphical interpretation of this, that will make more sense. So to start, pause the video here and first just evaluate this so that it's no longer in this definite integral form. And what we mean by that is if we were to integrate this, I'll do the first example, we get 1/2, we'll get 1/2 t squared plus 2t, and we want to evaluate that from 0 to x, and so our capital F of x is going to equal 1/2 x squared plus 2x. If we plug in 0, we're going to get 0, and so we're not going to subtract anything there. So pause the video here and try B and C and see if you get the same thing. That will come up in about 2 seconds. Right, so this one here, you would get 3/4 x to the 4/3 minus 12. And this last one here, we would get tangent x minus 1. Okay? So now that we can do this, what I want you to do is now take the derivative, so find f prime for each of these, and hopefully you'll notice a similarity between its derivative and what we saw in the original problem. And so again, I would pause the video here, do that real quickly, and then check your answer. And so for A, the antiderivative, or the derivative of this, would give me x plus 2. For B, it would be cube root of x. And then for C, the derivative of tangent x minus 1 gives me secant squared x. And so if you notice, our derivatives are identical to our integrands, except wherever there was a t, we now replace it with x. And so this takes us into the second fundamental theorem of calculus, which is this. If f is continuous on an open interval I containing a, then for every x in the interval, the derivative of the definite integral a to x f of t to t is f of x. So if this is just a regular x, all you have to do is substitute the x, and we have its derivative. If instead this upper limit is a function of x, then we're going to do the same exact thing. We're going to plug in g of x, whatever that function was in for f of t, but then we need to multiply by the derivative. And again, this is coming from the chain rule of this function here. And so let's look at some examples of that. So if we want to find f prime, well, because our lower limits here are all numerical values, I don't need to worry about the second piece. Remember, the integral of from a to b of f of t dt will be f of b minus f of a. And so if this is a constant, this will always be 0 when we take the derivative of it. And so for a, we're going from negative 2 to x, t squared minus 2t. If we want to find the derivative, I'm just going to replace the t with an x. So we get x squared minus 2x. For b, we're going from negative 1 to x, the square root of t to the fourth plus 1. Again, we're just going to replace the t with an x to the fourth plus 1. For c, we're going from 0 to x of t cosine t dt. So the derivative of f of x here will be x cosine of x. Now with d and e, notice here, right, we're no longer just going to x, we're going to sine x, which means we need to incorporate the fact that g of x is a function of x, and so we need to incorporate that derivative. And so with d, we're going to replace the t with the sine x, and so the derivative will be sine x times the derivative of sine, which is cosine x. E, again, we're going to replace the t with x cubed, and so that gives us sine x to the 6, because we're squaring the cube, times the derivative of x cubed, and that gives us 3x squared. And so these are the derivatives of these accumulation functions here. And so again, all you need to do, if it's going from a number to x, switch the t's or whatever variable they use here with x. If your upper limit is a function of x, just remember to multiply by the derivative of that function.